Hello children, welcome back, and today we are going to discuss the new topic electromagnetic induction. And before going to understand the various things related to electromagnetic induction, let us know first the very important concept, that is magnetic flux. What is the meaning of magnetic flux? So as per definition, it will be defined like the total number of magnetic lines of force crossing any area normally. So for example, let us suppose this is the uniform magnetic field and which is represented with the help of straight lines, and here I have one area such that its area vector is also in the same direction. Area vector is also in the same direction. Now, what is the flux going through this one? That is represented by phi, which is equals to B into A. Now, if the same area, let us suppose I am taking the uniform magnetic field such that I have the area now like this. Now, this is going to be the area vector, and this is the direction of magnetic field, and the angle between them, shall I call it in theta? Then the area vector along the direction of magnetic field is nothing but what? A cos theta. Therefore, what is going to be the phi now? B into A cos theta, and that's what sometimes it is simply represented as B dot A, the scalar product, ma'am. Welcome back, student. And in the last session we understood the different methods of inducing EMF, and there we understood two important things. One is by changing the magnetic field, how the induced EMF will be generated. We done two simple problems on that, and we also understood what is the concept of motion EMF, and so these are the formulas there we came to learn. What are they? So induced EMF magnitude is given as a BLV, and induced current is given as a BLV divided by R, and the delta Q, amount of charge that got induced, is equals to the ratio of the average change in magnetic flux divided by the resistance. This is the power dissipated, and this is the force experienced by the conductor when it is moving inside the magnetic field. Now, with this background, let us try to know now what is the motion EMF due to the conductor of any arbitrary shape. That we will see, and then we will move on for the doing 2-3 simple problems on the motion EMF concept. At the end, we will deal the EMF due to rotational conductor. Let us start now. The motion EMF due to any conductor of arbitrary shape. So here we have the concept. Let us suppose this is a uniform magnetic field having the value B, and there is a one conductor which is in some arbitrary shape like this, and so I am calling it as an AB. Okay, and so when it is moving inside the magnetic field with a velocity V, then what is the induced EMF? This is the question. So the induced EMF general formula is what? B into L into V. Here L is nothing but the length of a conductor, and for this case the length is nothing but effective length of a conductor. Therefore, what I can write? B into L, effective length of AB multiplied by the velocity. This is called as a induced EMF due to any arbitrary shaped conductor. I will give you one example problem also. For example, let us suppose there is a uniform transfer magnetic field. There is a uniform magnetic field here, and within this one conductor, semicircular in shape, with the radius of capital R, is falling with a velocity V. Semicircular in shape with the radius of R is falling with a velocity V. And so let us call this end as a P, this end as a Q. Now question is like this: what is the magnitude of induced EMF and where the potential is high? That means if Vp is the potential at the point P and Vq is the potential at point Q, what is the relationship between them? Either Vp is more than Vq, or Vq is more than Vp, or Vp is equals to Vq. That's what we have to find out. Well, let us start now. It is nothing but the conductor which is in semicircular shape. Now, for any arbitrary shaped conductor, what is the induced EMF magnitude? We understood here it as a B into L AB, effective length multiplied by the velocity. Here the effective length is nothing but R plus R, 2R. Hence, the magnitude of induced EMF is given as B is a magnitude of magnetic field intensity B multiplied by length is nothing but 2R, and it is falling with velocity V. Therefore, this is the magnitude of induced EMF. And where does the potential is high? How to find it out? So that we can find with the help of Fleming right hand rule. What is the Fleming right hand rule? So forefinger shows the direction of a field, the thumb shows the direction of a motion, and the central finger tip will shows one direction. From that end, the current will be, if that is a closed, current will be passes, or at that end we will have a more potential. So according to this one, this is a forefinger, this is thumb shows the direction of motion, and the central finger tip is showing towards this way. Therefore, at the end Q, potential is high compared to potential at point P. Therefore, VQ is more than VP. VQ is more than VP. The potential at the end Q will be more than potential at end P. This is what will be happen for this conductor. Well, now here I have some different case here like this. Now I am choosing the straight line conductor only, but it is moving with a velocity v inside the field like this, such that it is making an angle of theta. The direction of a motion is making an angle of theta with the length of a conductor. Now how much induced EMF will be generated? So this velocity could be resolved into two components. What are they? V cos theta and V sin theta. V cos theta will be along the length, and V sin theta will be perpendicular to length. V sin theta will be perpendicular to length. And this motional EMF formula E equals to BLV will be holds good whenever all the three components are perpendicular to each other. That means if any of these two, if any of either BL or LV or BV, if any of these two pairs, one pair, if it become parallel to each other, there is no scope for getting induced EMF. All the three parameters must be perpendicular to each other. And here V sin theta, length and magnetic field, all the three parameters are now perpendicular to each other. Hence induced EMF is given as B into L into V sin theta. This is the magnitude of induced EMF. If you understood this concept, you try to do this small problem. What is this is, I have one conductor which is like this, such that it is making an angle of 60 degrees. One conductor is there that is bent at one point, say this is the point P, such that the remaining two parts of this conductor are making an angle of theta which is equal to 60 degrees. And let us suppose they are moving in this direction with a velocity v inside the magnetic field of induction B. Okay, and here how much amount of induced EMF will be generated? How to find out? As I told you here, this velocity is making some angle with the line. What is that angle? This part is making an angle of 30 degrees. This part is also making an angle of 30 degrees. Now what will be the perpendicular components to the velocity? The perpendicular components to the velocity is nothing but, so if I choose this is the length L, this is the length L, what is going to be the perpendicular component? L sin theta will be perpendicular to velocity. L cos theta, L sin theta will be perpendicular to velocity. That theta is nothing but 30 degrees I told. Therefore, L by 2 is perpendicular to V. In the same way, this one also will be perpendicular to V. L by 2 will be perpendicular to V. Then, what is the total induced EMF? That is given as B into L by 2 plus L by 2 times of velocity is V, which is equals to BLV. This is the induced EMF generated for this conductor. There is a small difference between this case and this case. What is that? Here, the whole length is making some angle theta with the velocity direction, and I resolve the velocity into two components like V cos theta and V sin theta. And what about this case? The length itself is making some angle, and in this case I resolve the length into two components such that one of the component is perpendicular to velocity. Even in the same way how I have done here, I can approach here also. What is that? Let us suppose this is going to be the length L by 2. Okay, exactly at the center. Now, shall I resolve into two components? What I will get? L by 2 cos theta, L by 2 sin theta. And even this one also, L by 2 cos theta, L by 2 sin theta. So again, if I add the both, I will get the same, just like this result. So either velocity component which is perpendicular to length you can take, or the component of length which is perpendicular to velocity you can involve in this problem. You can substitute in this problem. Okay, right? Done. And let us go for two, three simple problems on the concept of motional EMF. Okay, right? So let us start here. So here I have the problem. So I will just give the description. Whenever it is necessary, I will write on the board. The problem is like this. There is a metal conductors which have the both ends connected to the capacitor. They said the capacitance is nothing but 10 microfarad, and they call this end as a P, this plate as a Q. The capacitor has a capacitance of 10 microfarad, and there are the two plates for it. One is P, another one is a Q, and they are connected to one metal ring, such that one end of this metal ring is hanged with one small conductor which can move with a velocity v inside a uniform magnetic field. So there is a uniform magnetic field here. In that it is moving, this conductor is moving with a velocity v, which that velocity is given as a 2 meter per second, and the length of a conductor is 1 meter. The magnitude of magnetic field intensity is 4 Tesla. From this information, they ask you to find out what are the charges that will be stored on the plate P and plate Q. How much charge and what is the nature of that charge that will be accumulated on the plate P and plate Q, that we need to find out. Well, let us start now. Since this conductor is moving with a velocity v, definitely I will have an induced EMF. What is the induced EMF? E equals to BLV. Here, length, velocity and magnetic field. All the three parameters are directly perpendicular to each other. Therefore, I can take this formula BLV. Now, what is the magnitude of magnetic field intensity? 4 Tesla. The length of a conductor is 1 meter. The velocity is 2 meter per second. So, how much? 8 volt. This is the magnitude of induced EMF. Now, the question arises, which end will have a higher potential? That we can do with the Fleming right hand rule. What's the Fleming right hand rule? So this is the direction of a motion, and this is the direction of a field. Therefore, this tip is showing this end. Hence, here I will have a higher potential, here I will have a lower potential, and correspondingly, here I will have a positive charge, here I will have a negative charge. Since I have a higher potential here, all the positive charge will be accumulated on the plate P, and since here I have a low potential, that means all the negative charge will be accumulated on plate Q, and here we can find how much charge will be accumulated on the plate P and plate Q. Well, let us do now. So what is the charge that will be accumulated on the plate? That can be given by the formula C into V, where C is nothing but 10 microfarad. So 10 microfarad multiplied by what is the potential here? 8 volt. So therefore, what we can get? 80 micro coulombs. The charge on the plate P is nothing but 80 microcoulomb, and the 2 it must be positive. So on the plate P, how much charge? Plus 80 microcoulomb, and on the plate Q, since everything is the same, the charge minus 80 microcoulomb will be stored on the plate Q. This is what the small sum. And now let us go for the next problem. We have like this. There is one straight, infinitely long conductor, and it is carrying the current of I, one constant current of I. And at the nearby it, there is a one conductor, a straight conductor, and which is having the length of A, and it is kept at a distance of B from the one end. The straight line conductor, it is at a distance of B, and it is moving inside the field with a velocity V. They are asking to find out what is the magnitude of induced EMF. This is what the question. Let me repeat again. Here it is an infinitely long conductor carrying the current I, and there is a one conductor whose length is A, and it is kept at the near of this conductor, such that One end is at a distance of B away from the conductor, and this conductor is moving inside the magnetic field due to this straight conductor with the velocity V. Now from this information we have to find out what is the induced EMF. So first of all, let us confirm that whether all the three parameters are perpendicular to each other or not. So velocity is like this, conductor length is like this, and the magnetic field will be into the plane of a conductor. So it will be like this. Already we know that whenever the current carrying conductor is carrying the current in this way, the magnetic field lines are into the plane of a board, which are nothing but into this conductor. Therefore, length, velocity and magnetic field, all the three parameters are perpendicular to each other. Therefore, induced EMF will be definitely generated. And here we have to observe one thing. What is that is, magnetic field intensity is not constant at every point on the length of a conductor. It is continually varying from point to point. Here it is more, here it is comparatively less, here it is comparatively less, and here it is the least. Therefore, magnetic field is changing along the length. Therefore, we cannot directly find out the induced EMF by using our formula E equals to BLB. Therefore, what we have to do? We have to apply the method of integration. What is the method of integration? That we will do like this. Let me draw the same diagram here, which is carrying the current I, and this is the conductor, and whose length is A, and one end is at a distance of B. Let me choose one small element here, which is having the length of dx, and it is at a distance of x away from the conductor. There is a one small element I am choosing whose length is dx, and this element is at a distance of x from the straight conductor. Now, the induced EMF in the small part, which is given as a dE, will be equals to B into L is nothing but dx. The velocity is V. What is the magnetic field intensity at this point from this conductor? And since it is an infinitely long conductor, B equals to mu naught I by 2 pi x. So mu naught I by 2 pi x into dx multiplied by the velocity. Now let me take out all the constants. Mu naught IV divided by 2 pi and 1 by x dx. This is only left out expression for us. Now let us try to find out the total induced EMF by applying integration technique. So what is the integration technique? Integral. What are the limits for this integration? The value of x is varying from this end to this end. We have to cover here, what we have to do is, we have to cover the total length of a rod, and whose range will be from B to A plus B. The range of this conductor is nothing but B to B plus A. From this conductor, one end is at a distance of B, other end it is at a distance of B plus A. Therefore, its range is nothing but B to B plus A. And that alone we are going to substitute here. So, the minimum value of x is nothing but B, the maximum value of x is nothing but A plus B, multiplied by mu naught IV divided by 2 pi into 1 by x dx. Finally, what we will get? Mu naught IV divided by 2 pi log x to the base C from B to A plus B, and upon substituting it, what we will get? Mu naught IV divided by 2 pi times of log of A plus B divided by B to the base C. This is going to be the total induced EMF that generated within this rod, which is moving with a velocity V. Okay, so now we are going to see one interesting question now. See this question, it will be quite interesting. First of all, I will write what is the question, and then I will try to explain you. A square loop Right. So try to understand the question first. What is given here? A square loop of side 12 centimeter. So let me try it. Let me try to draw one square loop here. So here is a square loop whose side equals to 12 centimeter. And with its sides parallel to x and y axis. That means one side is along x axis and one side is along y axis. With its sides parallel to x and y axis. Is moved with a velocity 8 centimeter per second along positive x direction. That means it is moving this direction with 8 centimeter per second velocity. And in an environment containing magnetic field along positive z direction. That means it is out. It is out like this along positive z direction. The field has a gradient of 10 power minus 3 Tesla per meter along negative x direction and with an increasing along the negative x-axis. What is the meaning of it? The field strength is keep on increasing in this direction with when you are moving from one end to the another end, from positive end to negative end. I mean from the right hand side to right hand side to left hand side. When you are moving in this way, the field strength is keep on increasing at the rate of 10 power minus 3 Tesla per meter and also decreases at the rate of 10 power minus 3 Tesla per second. So it is keep on increasing in this manner and also decreasing at the rate of 10 power minus 3 Tesla per second. So already field is existing in this direction with an increasing magnitude. And after some time what happened? It starts to decreasing at the rate of 10 power minus 3 Tesla per second. Now they are asking to find out what is the induced EMF in this loop. Okay, then now let us try to start the problem with already known formula for us. What is that? The magnitude of induced EMF is nothing but d by dt of BA cos theta. This is the very well known formula and that's what you will get. The first glance you will get this formula only in your mind. Well, here what is the theta? The area vector and magnetic field both are parallel to each other. So cos 0 equals to 1. What we are getting? D by dt of B into A. Where A is nothing but area, B is nothing but magnetic field. Now the A can be taken out because A is the constant. A into dB by dt. This is the induced EMF due to the rate of change of magnetic field. The rate of change of magnetic field. So here in the question, since the magnetic field is given, it is decreasing at the rate of 10 power minus 3 Tesla per second, we can able to find out what is the induced EMF within this loop due to the change of magnetic field intensity with the time. And not only it is varying with the time, it is varying along the distance also. Since the loop is moving like this, these lines, these conducting parts are cutting the magnetic field lines of decreasing direction in this way. Now what will be the magnitude of induced EMF because of this motion? That can be obtained like this. The same expression, let me take here, which is nothing but E equals to A into dB by dt. Now, shall I try to make this small modification for this? Well, A into dB divided by dx multiplied by dx by dt. Anything wrong? Just added the dx term into this expression. Now, this will be nothing but what? A into V multiplied by dB by dx. Where dB by dx is nothing but the gradient of magnetic field. Since as it is moving in this direction, it is moving across the gradient magnetic field. The induced EMF will be nothing but AV into d by dx. The net EMF that generated in this loop is nothing but the sum of the EMF due to the time varying magnetic field and the gradient of magnetic field. The net sum will be due to the sum of the both. Therefore, we can write like this. The total EMF, shall I clean up this part? The total EMF will be equals to A times of dB by dt, the induced EMF due to rate of change of magnetic field, plus A into V into dB by dx. This dB by dx is nothing but gradient of magnetic field. Now, by taking A as a common, the dB by dt they have given as 10 to the power of minus 3 plus what is the velocity? 8 centimeter per second. So 8 into 10 to the power of minus 2. What is the dB by dx? That itself they have given like 10 to the power of minus 3. 10 to the power of minus 3. And A is given by the side, how much they have? 12 centimeter. So therefore, what you can write now? 12 into 12, 144. 144 multiplied by the 10 to the power of minus 4 into 10 to the power of minus 3 plus 0.08 into 10 to the power of minus 3. By substituting all these values, we will get 129.6 into 10 to the power of minus 6 volt. This is the total. That means 129.6 microvolt. This is the total EMF that could be generated in this loop. Okay. So here important point is what? There may be some questions with the variation of magnetic field with the time, the variation of magnetic field with the distance, and there may be questions like the variation of area. The area may be changes with the time. Sometimes in the constant magnetic field, there may be some question like where the area itself will be changes with the time. So according to given context, we have to modify the expression. If possible, we have to add 2 more EMFs. Just like in this case, here we have the 2 cases. One is varying magnetic field and variation of magnetic field with the distance. And the net EMF is nothing but sum of the both. Like this, we have to add all. Okay. Well, with this background, let us move on for the last context, that is the EMF due to rotational conductor.